All right. So, so the last time, do you have any questions before I start?
No?
Okay. So the last time we started to talk about the instantaneous center of zero velocity, and we studied some applications on how to determine where is the instantaneous center. We identified that there's four ways to identify the instantaneous center of zero velocity. And this is the last application of on the instantaneous center of zero velocity for the pulley system. So let's solve this pulley system using what we learned from before in the in chapter 12. So for example, if I'm like giving you in this problem that this weight F will move down with Vf equal to 6 feet per second. So what is the velocity of A? So actually what we do, we identify a fixed position like this. So we know that this point is fixed and this point E and point D and also this point. And then we start to measure to the moving points. So what is moving here is B, C, and F. So this is the three moving points. Yeah, point A is moving, but it's totally related to point B. So if B is moving up with 1 feet per second, A will be moving up with 1 feet per second. So if we got VB, we will be able to get the velocity of block A. So let's have this, so this will be YB, and point C is moving as well. So we will have YC, and also this point is moving, and we will call it YF. So we have three unknowns, YF, YC, YB, and we have the velocity of F. So let's get the velocity of C and velocity of B. So if you are solving this, you have two cables. You have this cable until point C, and the second cable start from C like this up to this point. So we have two equations here. So the first equation will be the yellow cable, and yellow cable length is YB, this YB, all of these lengths from here to here, and then from here to here, which is YB minus YC. So YB minus YC will be equal to constant. So we will have 2YB minus YC will be equal to constant. And from here, if we take the time derivative d dt, so we will have 2VB minus VC will be equal to 0. So this is our first equation. Let's get the second equation from the second cable. So the second cable is the green one. So we have, this is from here to here. This is the variable, and from here to here, and from here to here. So we have 3YC. And the third one is from here to here, which is the YF. So 3YC plus YF will be equal to constant. And we agreed last time we will exclude the things that is not varying, such as this and this and this. So these is not going to vary with the our equation, and we put constant rather than putting the length of the cable. And from this, if we talk the time derivative, it will be 3VC plus VF will be equal to 0. So VF, this is the second equation, and let's set these equations in different forms. So let's get the VC. So now we can have VC equal to 2VB from this equation. And we can substitute with VC in this equation. So we will have 3 multiplied by 2VB plus VF equal to 0. So VF will be, let's write it here, VF will be equal to negative 6 VB. Oh, let's get VB because we have VF. So VB will be equal to negative 1 over 6 VF. So it's the same, like if you write it VF equal negative 6 VB, so you divide by negative 6, so it will be negative 1 over 6 VF. So VB negative 1 over 6 VF, we have VF is 6 feet per second, so it will be negative 1 feet per second. So this is the velocity of this. So if VF is going down, VB will going up with 1 feet per second in the opposite direction because our positive is going down. So let's solve this problem with the instantaneous center of zero velocity mentality. So let's see how can we do this. So first thing, if you want to do that, you will have to understand the problem, understand the motion of the problem, like you know that this body F, if the body F is going down, so this cable will go down and this cable will go up, which will push. So this will go down and this cable will go up. And this, if you follow this cable, you will find that this will go down and this will go up. So VC will go up. And then you will go follow the same cable. So this one will go up and this one should be going down like this. So this is how the cable is moving, and this means that the VB will go up. So you understand how the problem will work. The second thing, you will need to determine the instantaneous center of zero velocity for as much bullies as you can. So for bully E and bully D, it's very easy because we can see that this point is not moving. So the center of these pulleys are the instantaneous center of zero velocity. For policy, it's quite difficult because you have many points is moving. You have this point is moving up, and this point is moving up, and this point is moving down. So it's a little bit tricky. So we will leave it for now. But for bully B, we know that this cable is fixed here, and we know this point is something like you have a wheel is moving in the ground. So the ground has a velocity of 0, which is touching the wheel. So this point B is the instantaneous center of zero velocity. Similar, if you have a cable that is attached to a fixed roof or something, and then this point is an instantaneous center of zero velocity. So this point is an instantaneous center of zero velocity. Okay, so if this point have v is 0 and we want to know, we know that this pulley is going up, so we will have VB like this. If we draw a line tip to tip and tail to tail, so here is the tail, and we know the ratio between this is R and this is 2R, so we will know the velocity at the end of this pulley. If this pulley has VB here at the center, so at the end of this pulley, we will have 2 VB. And this 2 VB will be transformed to VC because it's on the same cable. So all this will go. Here we will have 2 VB. And this will keep going up 2 VB up to this pulley. So you will have 2 VB here. And you know that this is an instantaneous center of zero velocity, so you can draw tip to tip and tail to tail. So you will have 2 VB here. And this 2 VB will go down until like with the same cable, like this, 2 VB. Right now we know the vector of two velocities on the body, so we can draw also another line from tip to tip and tail to tail, and you will be able to know the velocity at the end of this pulley. And actually, this is the instantaneous center of zero velocity here. So you have 2 VB here and 2 VB here. If you solve this triangle, you will find that the velocity at the end will be V6B. You can solve it actually easily. So this part is going to be equal to this one, and this one will going to be 4B after you do some geometry analysis. And then V6P will go up here because it's on the same cable, so 6 VB, and you know that this is a 0, so you will draw a line tip to tip and tail to tail, so you will have 6 VB. So the velocity of the cable here will be keep going down 6 VB, and this will be equal to VF. So we will have from here that VF will be equal to 6 VB, and we can know. So we know that VB is going down, and this one, VB is going up, and VF is going down. So we know the directions. So we can get VB, which is VF over 6. So it will be 1 feet per second. So this is how we can track the pulleys using the instantaneous center of zero velocity. Does anybody have any question on this problem? How we track the velocities, how we get the instantaneous center of zero velocity? All right, so let's solve one last problem on this section from this chapter. So let's solve this example. So for this example, it's called multi-bar linkage. So you have 3 bars that pin to each other at different locations. Some points are restrained from motion or restrained from translation, but they are allowed to have fixed axis rotation, such as point O and point B and point C, sorry. Point B is free and point A is free. So here in this problem, you are given all the geometry. So you are given all the geometry needed to get the distances between C and B, B and A, and also A and O. And you are only given the omega of the body CB, and it is equal to 2 radian per second. 2 radian per second. And you are asked to get the omega of AB and the omega of OA. So you are given only the left body BC, and you are asked for the other information or the other omegas of the other bodies in this problem. To understand this problem, I want to show you an application. Yeah, so here's one of this is the same problem drawn by Dr. Dan Baker, shows how is the motion look like. So if you have the body CB is moving down, so that means that the omega is counterclockwise, and I need you to notice the body AB, how it moves. So the body, when BC do counterclockwise rotation, AB will do clockwise rotation, and the body, so let's see, what do you think about the body AB? So if we have B is moving this way, yeah, it will be clockwise, and also body OA is moving clockwise, like this. So let's have this in our problem here. So actually, if we have omega in this direction, we will be having VB going down. Actually, let's don't mess with this problem and have it here like this. Okay. So we have omega CB equal to 2 radian per second. And we have this O, A, B, and C. Okay, let's draw the directions of the velocity. So if we have omega CB is going this way, so we will have the omega of the other body. This one will be going this way. So this is omega AB, and AOA will be moving this way. All right, so, and from here, we can get that VB with respect to C, and C is not moving, so if VB will be equal to VB with respect to C, it will be in this direction. So this is the VB vector. And let's get the velocity at B. Okay, so you have 2 directions to solve this problem. Either that you are familiar with the directions of the velocities and the omegas from the body geometry, and it's a very easy to do it in terms of velocity and omegas, but it will be more complicated if you have an acceleration alpha and the a. So I would recommend to go into the other way, which is to solve it with vectors. So let's do both. Let's do if we solve it with vectors, or if we solve it with the just like the scalar form. So VB vector will be equal to VC vector plus VB with respect to C. From here, we know that VC is equal to 0 because it doesn't move. So VB vector will be equal to VB with respect to C, which is the omega of BC crossed by RB with respect to C. So let's see what is the direction of the omega VB. We have 2 radian per second, and if you use your right hand rule, it will be in the k hat direction, and it's in the positive k hat. And let's cross this with the RBC. So RBC is this vector. It's in the negative I hat direction. So, and it has a distance of, if you look here, 75 millimeter. So you can have this as 0.075 if we solve it with meter, and it's in the negative I hat direction. So we will have negative I hat. And if we multiply this cross product, you have I, J, and K. If you multiply K by I, it should give you a positive J hat. If you multiply K by I, it will give you positive J hat, but we have negative outside here. So it should give you 0.15 and it will be in the negative J hat direction because K by I is positive J and we have negative. So, and this is what we have. VB is in the negative J hat direction. So from verse, we can use the scalar form VB is equal to omega multiplied by R, and the omega is 2 multiplied by R, which is 0.075, and it will be 0.15 meter per second, and you should indicate the direction on the drawing so I can know that you predicted the direction right. So this is VB. Then we need to get the omega AB, and to get the omega AB, we will use the calculated VB to get it. So let's see how can we get it. So to get the omega AB, we need to identify the instantaneous center of zero velocity. So we will use the velocity of B and the velocity of A to get this. So knowing the direction of the omega A, we can predict that the velocity VA will be in this direction. And we can draw a perpendicular to B and a perpendicular to A. So this will be the instantaneous center for the body AB. So if we want to get the velocity of B from this instantaneous center, so VB will be equal to the omega AB multiplied by RB with respect to the instantaneous center. So we know VB right now here, 0.15 meter per second, because we got it from the right member, but we don't know omega AB, but we know the RB with respect to the IC. So RB with respect to the IC is this vector, which will be 250 minus 75 millimeter. So it will be 0.175, and then we can get omega AB, and this should be 0.857 radian per second. So does anybody know, is it in the positive or the negative direction, the omega AB? So the omega AB is curling in this way. So if you use your right hand rule, it will be in the negative K hat direction. And VB, you should write it's in the negative J hat direction. Okay, so we got VB. We can also get VA from the member AB. So VA will equal to omega AB multiplied by RA with respect to the instantaneous center of zero velocity. So this will be equal to omega AB, which is 0.875 multiplied by RA. So this is 50 millimeter. So this will be 50 millimeter. So this will be multiplied by 0.05. And this should be equal to 0.043 meter per second. And this will be in the positive I hat direction. Okay, so we got VA from this member, AB. So let's use VA to get the omega of the member OA. So VA is equal to the omega of the member OA multiplied by RA with respect to O. So this should be VA, we know it, it's 0.043, but we don't know omega OA. And we know this is 0.1. And this should give us that the omega OA is equal to 0.43 radian per second. And if we use our right-hand rule, so it will be in the negative k hat direction. So we have VA here is equal to 0.043 meter per second. And let's box it. So yeah, so this is how we get it. So we start from the member that has all the information needed to start and build the velocity equation. So we start from BC, and then we got the velocity of B, and then from B, we got the omega of the body AB, and from the omega of the body AB, we got the velocity of A, and then moved from A, we got the omega of OA. So this is how we start the problem. If you start the problem from the member OA, so you will build an equations with a lot of unknowns, and we don't have the inputs to solve these unknowns. And you start building some equations, and sometimes it's right, you can do it, but at some point, maybe you feel confused, you are having unknowns, and you don't have inputs to put to get these unknowns. So it's better to start from the members that you know what is the omega for these members. Does anybody have any questions so far? Okay, so I want like to show one more thing. Here, yeah. So what if we have two bodies attaching together? Like if you have a body OA, have another body AB attached to it at point A. So if the body OA is having a certain omega, like let's assume that body OA has omega of 1 radian per second, and it's positive, so it will be in this direction. But the body AB doesn't have an omega, so it will only, so the omega of the body AB will be similar to the omega of the body OA. But if the other body AB is rotating about A, like this, so we are adding omega to the other body like this. And similarly, alpha, like let's change it something like that. So this is rotating in a different way than the other body. So let's formulate this problem. If we have just the other bodies moving, so we have only the omega of this body. As we construct relative velocities, and we said, let's have this as something like that. And let's make another center here. And let's say that we have this, and we have this. This is O, A, B. As we said that the velocity of A equal to the velocity of B plus the velocity of A with respect to B. Also for the omegas, sometimes if you want the omega of this body and you have OA is having an omega and AB is having an omega with respect to OA. So if you want the omega of AB, it will be equal to the omega of OA plus the omega, and all of these should be has a vector, and plus the omega of AB with respect to OA. Like how much rotation is making this body AB about this point along with this one. So we sum both of these omegas, this one and this one. If this in the counterclockwise, so it will be with negative direction, so we can get it. And similarly, the acceleration of AB will be equal to the acceleration of OA plus the alpha AB with respect to the OA. So just like when you have a problem, just determine if you have two bodies that having different omegas and they are attached at one point and are related, so you will need to construct these two equations. All right, so with this, let's move to the last, I think, or the one before the last, chapter 16.7. Which is the relative motion analysis. We will talk about the acceleration. Okay, so for the acceleration, as from the velocity, we said that VB is equal to VA plus VB with respect to A. If we talk the time derivative of this equation, ddt, it will be AB vector will be equal to AA vector plus the AB with respect to A vector. And if we want to draw this like what we did the last time, it will be something okay. So if we have this point A, this point B, and this A having this path, and this B having this path, and we know that AA, so right now we are dealing with acceleration, so AA is in this direction, and AB is in different direction like this. So what we did last time is that we divided this into two, and we said that this is AA, and we will have another AA here, and here we will assume that this point is a fixed axis rotation, and you have in A B with respect to A something like this, and finally the sum of these will give us the AB will be equal to the AA plus AB with respect to A. So something like this. So this is what we did the last time. However, here it's a little bit complicated as ABA and AA and AB, all of them has a normal and tangential component. So this will have a tangential and normal component, and all of these will have normal and tangential components. So if we want to get it, and we did it before, and we proved that ABE, the acceleration in the tangent for any member, like this is just for example, B with respect to A, it will be the alpha of B member BA plus, cross product by RB with respect to A. And the AB with respect to A normal, it will be equal to the omega crossed by the omega crossed by the R. So all of these AB or BA. And this is RB with respect to A. And we proved that this will be negative omega square of AB multiplied by the vector RB with respect to A. So this is the tangential and normal components, and that's actually what we need to know. And we can put this back in the equation that the EB vector will be equal to the AA vector plus alpha BA crossed by RB with respect to A minus omega BA square multiplied by RB with respect to A. So this is the acceleration equation that we need right now to get the acceleration at B. And let's just see how this will look like in terms of problems. So like, for example, if we have this two-bar linkage, and this bar is been here, you have another bar attached here, and this bar is having like a box here that is attached to the cylinder that only allows this bodies to moving in the X direction. So what if we know the AC here, like here at this point, this is, let's assume that this is A, B, and C, and you know the direction of the acceleration at C, and you know also the magnitude as well. That means that this body is, this one is moving this way, and this body is moving this way. And it is different than the velocities because the velocity will only have a one tangential component. But if we want to know the acceleration at B, we will need to put a tangential and normal acceleration. So we will have at B, if this body is moving this way and assuming it's accelerating, like we have the alpha is in this direction. So we will have AB with respect to C tangent in this direction, and we will have AB with respect to C normal in this direction. So this is how we can get at B. And if you finally want to know the total acceleration at B, you will get the root of the sum of the squares of the tangent and normal components, and you might find that the AB is in this direction. So it's a little bit different than the velocity because we have the normal components, and it changes everything in terms of the direction and the magnitude. So this is how different it is, and actually we use the alpha to get the this AB. So how about like see another example on this? Like what if we have something like this is the ground. And this is here. And you have another body here that has some kind of roller that can roll on this ground. And you know that the omega of this body and the omega, like, you know that this body has an omega in this direction. And actually, let's draw it in a better, if this body, this is counterclockwise. Okay, this is omega AB. And also you have, this is the direction of the alpha AB. So the body is accelerating. And also, you know, the omega of OA, let's call this O, A, and B. And you know the alpha of OA, like this. So let's map the acceleration and the velocity vectors. Let's start with the velocity vectors. So you know that this one is bend, so you will have at A, so you'll have the acceleration, the velocity of A is perpendicular to this body, like this. So this is VA with respect to O, because the omega is going in the counterclockwise direction. And if you want to get the tangent acceleration, it will be also a tangent is in this way because it's with the direction of the alpha. And if we want to get the normal acceleration, it will be something like this. So this is a normal. So we mapped the acceleration at A. So how about mapping the velocity and the acceleration at A with respect to B? So with this, we know that with this omega, we know that this body will be moving this way. So this is the VB. And you know the direction of the omega AB, so you can get the velocity of A with respect to B, and it will be something like this. So perpendicular to this body, and in the direction of the omega, so it will be VA with respect to B is in this direction. And similarly, you will have the AA with respect to B tangent is in this direction because it's in the direction of the alpha. And if we want to get the normal acceleration, so it will be A with respect to B normal is in this direction. So this is how we can map the acceleration and the velocity of A with respect to B. So you should be able to do this because next quiz you will be asked to map the instantaneous center of zero velocity and also some questions about how you can map the acceleration and velocities based on given omegas in alpha's direction. So this is how we can do the mapping here. Let's do another example. So if we have a disk like that, and there is an arm, like let's assume that the center is here, and this disk is rotating about this one, and we have an arm here at this point. And we have this disk is rotating. So let's assume this is point A, and the point here is B, and this is point O, and this disk is rotating with omega OA, and have an alpha is in opposite direction, so this is alpha OA. So let's map the velocities and acceleration at point A and point B, assuming that the body AB is not rotating about A. If the body AB is rotating about A, so we will have to apply this equations because we have two omegas of two bodies, so it will be a relative angular velocity. So let's assume that the body AB is not rotating and the only rotating is the disk about point O. So for the velocity VA based on this omega's direction, so VA will be going up like this. And the tangent acceleration, so let's put VA, and the tangent acceleration will be going down because the alpha is in the opposite direction. So AA tangent will be going down, and always the normal will be going towards in the negative direction of the radius. It will be something like that. So we map the acceleration and the velocity at A. So let's map the acceleration and velocity at B with respect to A. So for B with respect to A, we will have VB will be something, sorry, VB with respect to A, it will be something like this because the body is moving this way. And if you draw the vector RAB and do the cross product, so you will find that VBA is in this direction. So how about the alpha to get the tangent acceleration at B? So the tangent acceleration at B will be something like that. So AB with respect to A, because alpha OA is in opposite direction, will be something like this. And the normal, so it will be something like that. A, B with respect to A normal, and this is tangent. So we mapped the acceleration B with respect to A. So what if I want only VB? How can I get it? So right now, we can write that the VB will be equal to VA plus VB with respect to A. So right now we have VA is going up, and VB with respect to A is going in the positive I direction. So VB will be something here. So this is VB with respect to A, and this is VA. So this will be VB. So VB will be something here, and I need to solve the problem to determine the exact direction. Similarly, you can get AB with AB, which will be equal to AA plus AB with respect to A. And from here, you can get the direction of AB with respect to A. And from here, you can get the direction of AA, and then you sum the vectors, these two vectors, to get the acceleration at B. If you are given another omega for the body AB, so like you are given in the problem that this body is moving with this alpha and this omega, and this body is moving, has a different alpha and different omegas, so it will be very complicated, and we can solve it in a scalar form. So we'll need to move back to the vector form so we can solve it right. So it will be, it has a lot of vectors, so we'll need to do a lot of summations. And also I would encourage to solve the main problem with vectors, because as you can see, it's a very messy here. You will have to solve point A, and it has velocity, acceleration, tangent, normal, and also for VA. So I would encourage you to use the vector form. Does anybody have any questions so far on this concept? How to map the velocity vectors, the acceleration vectors? Okay, you should train yourself well and do this mapping, because at least half of the points for the next quiz will be devoted for this concept. Okay, so let's move to a different topic, which is a chapter 16 point, I think this was a chapter 16.7, so we will be in a chapter 16.8. Rigid body relative motion was a slipping. Okay. So here I want to differentiate between three terms: non-slipping or no slipping, slipping, skidding. So let's differentiate versus rolling. Let's say here, number one, rolling without slipping. Okay, let's have an example here. If we have, let's assume that your car, this is one of the wheels in your car, and this is the ground, and this is the center of the wheel, and you have a point B, and your wheel at time t start to roll like this and came at this position. So when this wheel start to roll with certain omega, this point after you, if there's no slipping, when I mean slipping, like the wheel is not rotating on itself, so this point will be at some location here. So if we are saying this is point P, so point B will be here. So the wheel moved from here to here. So if there's no slipping, the distance from this point to this point, let's call it delta x, should be equal this distance s if there's no slipping. So delta x will be equal to delta s, this part. So if I want to get the delta x, so I know that the center of this wheel is moving with a certain velocity v, and I can get the v here by multiplying the r. I know this is an instantaneous center of zero velocity, and knowing the omega, I can multiply r by omega to get this v. So I know this is the velocity, and similarly here, this is the velocity. So if I want to get delta x, I can divide velocity. I can multiply velocity by time, delta t. And as we know that v is equal to delta x over delta t, I just like multiply delta d by v. And if I want to get the delta s, if I know the theta, from here to here, delta theta, and multiply delta theta by r, I will be able to get the S. So delta theta multiplied by r, and I can get the velocity here. V will be equal to delta theta over delta t multiplied by r. So the velocity will be equal to the omega r. And this is what we know from here. Like V is equal to the omega of this body multiplied by r. So this is if rolling without slipping. So let's assume that you are moving on ice, rolling with a slipping. If you are moving on ice, sometimes your wheel will rotate on itself without doing any motion. So if this happen, like a car wheel spinning on ice. So spinning, that means that spinning is faster than translating. Your car is not translating, is not making this, but it keep rotating. So this B keep rotating like this without any motion in the delta x direction. So that means that the delta x will be less than delta s. So your body is keep rotating, but without doing any translation. And that means that your velocity will be less than r omega, because your body will keep doing r omega, but it's not moving. So the velocity is almost zero, while you have your body is having an omega. And when you multiply omega with r, it will be more than v. So this is for the rolling with a slipping. So what is the opposite of this? Is the skidding. So for skid is that there's no spinning, like you are on brakes and you are down the hill, and your car is keep sliding on the surface going down without doing any rotation. So there's no spinning here, but the wheel is skidding. So it keep moving in the delta x direction and making a translation without the wheels is rotating. So here we can say that the velocity, the translational velocity, is more than the r omega. So this is the difference between these three concepts. And if we are handling relative motion with the slipping, and this is the topic that we will be discussing over the next 10 minutes. So relative motion with the slipping. Okay. For relative motion with the slipping, we have same equations, but we will add new term to the equations. Like if we want to, we have from previous that VB is equal to VA plus VB with respect to A. So this is if there is no slipping. But if we have a slipping, this equation will be transformed to be V at B will be equal to V at A plus VB with respect to A plus VB with respect to A. And I will explain this later. So we will have another term here, and we call it as the slipping term. Similarly, for the velocity, we will have AB vector equal AA plus AB with respect to A, and this no slipping. But if we have slipping, this velocity, so let's say here with a slipping, equal to AA plus AB with respect to A, and this will be plus A, B. And this is called the sliving term. So the derivation of this equation has a very long context here. You can actually check it. So, but I will not be able to explain all of this in the lecture. So I'm not like, I will use the final equations, but you are more than welcome to like read this and how can we derive the equation of the velocity and the equation of the acceleration based on this concept. And I will not asking you how we derive these equations, but what we need to do is just to know, understand what is each term of this equation mean and how can we use it and solve our problems. And this is totally what I want from the concept of relative motion with sliving. Okay, let's understand this concept. So I will explain this concept. Actually, I have some pictures here, down there. Yeah, so here. Okay, for this problems, this three problems is considered motion without slipping. Let's see why it's without the slipping. So for body B here, sorry, for the this one, let's call this as number one. So the point B is allowed, cannot slip because it's attached to the body here. And if this is making an omega, so this body will be here and C will be move maybe at something there and the body will be something like that. So there is no slipping here and we can apply the equation that VB is equal to V at A plus VB with respect to A, assuming this is point A or something. And similarly, this one, from the first glance, you can assume that the point B is slipping on this bar, but actually this bar is a fixed path, is not moving. So if the point B is slipping on a fixed path, so we can solve it with the equation without slipping. So we can say that VB is equal to VA plus VB with respect to A. So we can solve this from knowing the velocity at point A here. Similarly here, the point C is slipping on a fixed path, so we can also solve this with the velocity of B, solving it with the same equation. But what if the path is moving, like this body B is slipping on a moving path like this? So what if we have this ring, and this ring is rotate, and B is allowed to slip on the body, and this body is moving, like the path that the color B is move on is keep moving. So we solve this by this concept. Like let's assume that this is our ring. And let's assume that we have a point on the ring and let's call it B. And let's get the color outside the ring here. So this is our color and point B is on the color. So point P is on the ring and B is on the color. So what happens here is that point B is slipping on B, like at some point the color will be here. So point B will be here and point P will be down there. So B is moving away from P. So let's put the equation here. So what we have is that we can have the velocity of B will be equal to the velocity at A here plus the velocity of P with respect to A. So this point, how much it moves with respect to the point A out there. So knowing the omega, so this is VB with respect to A, plus the slipping term. So all A and B are on the same body. Like here, you have the point B is below this color, and it's on the same body such as A. So the third term is VB with respect to A. So how is the color B is moving away from B? Like from here is that the B is moving in this direction and B is moving in this direction. So we need to know VB with respect to A. And you should apply the rule that we learned from before in the relative velocity. For the subscript, B will be equal to A multiplied by B over A multiplied by B over A. Sorry, this should be A with respect to B. Oh, this should be VB with respect to A. And this should be B with respect to B. Yeah, because I was talking about this, how much B is moving away from B like this. So if we put B, so like now I did some typo here and I put different one. So if I want to check, I put the subscript and multiply them together. So you will find that A is canceling A and B is canceling B. So you will find that B is equal to B. So that means that I construct my equation right. And if you want to do further check, you should check that point A and point P are on the same body. Like you have the ring here and you have point A here and point B here. So point A and B are on the same body and you have a color here with point B is moving away from point P. So this is how you construct the equation. And similarly, you should construct the acceleration equation, like AB will be equal to AA plus AB with respect to A plus AB with respect to B. And let's see the other one. So you have a bar, and the color C is a slip on the bar AB, which has an omega and alpha. So if you have this bar like this, so you remove the color. Let's put the color outside here. Okay. Just taking a section here and point A somewhere here, and let's put point B just down or below the color. So we will have B here and the color have B here at this location. And B at some point when this arm is moving, arm AB, C, the color at C, so let's make it the C because that's the name here. Or you can call it B like you can this, so you don't get confused. And let's assume that this B. Okay, so A and B are in the same body, so you will have that the V at B will be equal to the V of A plus VB with respect to A, and we can get this from this omega, so this is VB with respect to A plus VB with respect to B. How much is this color B is moving away from this point blue? Like at some point this color will be here, so we'll have B at this location and the other B at this location. And similarly, this one, you will have an arm with a small groove here. And let's put B here, and you have A down there, and you have a point on the disk O like this, and let's call this P. So there's a pushing force that allows this disk to move this way. So this will keep going down, and B will slip on P. So you will have VB will be equal to the velocity of A plus the VB with respect to A, this point with respect to this point. If we know that A is moving this way, so this will be VB with respect to A plus VB B with respect to P here. So at some point, this point will come here, but here is the point P. And this is the point, the other P. So this is how we can construct our equation. So this is just like a background, and I'm going to solve a problem and do some applications on this concept in the next lecture. Does anybody have any questions on the slipping? I know it's difficult, the one with the slipping, but just like use the equations and you watch this video one more time to understand how you identify which one is B, which one is P. So to construct the equation well and solve your problem in the right way. Does anybody have any questions? All right, guys, see you tomorrow.
See you tomorrow.